Okay, the next couple of lessons are going to focus on model building. So a critical part of optimization is being able to take a scenario and build the model out of it. And as we're going to see, these models can get fairly complex, but being able to understand the process and being able to methodically go through and build the mathematical equations out of your model is an important skill to have in doing optimization. So for this one, we're going to start off with you trying it. Go download the file AMS 2940 model building one background and try it. Now you don't have to solve the problem at this point. The important part is to write down the mathematical formulation of the linear program, making that transition from the scenario to the mathematical equations. Once you've done that, try to solve it if you can. See what you get for your solutions. But the important part at this point is the formulation. Okay, so now that you've given that a try yourself, we're going to take a look at a solution to it. Now there's 3 steps to this problem. Okay, this slide says that there's 2. There's actually 3 steps in the problem. So the first one is where we can't store things from month to month. Whatever we buy, we have to use. The second one allows us some storage from month to month. And the third one creates a little bit more flexibility. It has a reserve that we can use. And we're going to see what the implications are of each of those. So first, when there's no storage, what we have are 3 independent problems. Okay? So you can solve it for January, you can solve it for February, and you can solve it for March. And you can solve each of them independently. Or if you want to, you can create a larger problem that handles all 3 months simultaneously. So what we're going to do is we're going to take 1 month first and look at 1 month. Now, traditionally when you're doing these types of problems, it's quite often a good idea to try a simple version of the problem and build up from there. So in this case, if we were given the scenario 3, where everything is on the table, one strategy to solving this problem would be to start off with saying, okay, well, let's assume that there's no storage. Can we solve that? And then can we add other things in? So taking a problem and kind of breaking it down into simpler parts and growing it slowly is actually a strategy that you'll often use when solving these problems. But in this one, we're going to start by looking at a single month where there's no storage from month to month. Now I'm going to step through the variables that I used and the equations that I use for the optimization function or the objective function and for the constraints. Note that these may not be unique. You may have a slightly different way of formulating this program which would give the same solution. Sometimes there's different ways to think about it that will give a solution. So even though your solution may not match 100% what's here, it is possible that what you did will give the same response, will give the same answer. So first off, always a good idea to start with your variables, write them down explicitly. So for the month of January, we have different quantities of the 5 oils that we purchase, and then we have the quantity of the final product produced. Now right away, you're going to note that there is a way of simplifying these variables. You can write this problem without actually using y. I put it in here for a reason because it's going to carry over to the next problems, but you don't have to have that variable in there. And we're going to see that there's an equation in here later that essentially makes it redundant. So now let's look at our objective function. What's our objective function? We're trying to maximize profit. What's our profit? It's $150 for every ton that we produce minus the costs of the components. So the profit function is pretty straightforward. Subject to. Now, what are our constraints? Our problem says that oils of type 1 and 2, the vegetable oils, we can only produce 200 tons of them a month. or we can only handle refine 200 tons a month. So the sum of the first two variables has to be less than or equal to 200. The next three oils, the non-vegetable oils, our problem says we can only handle 250 tons of them a month. So there's our constraint for that one. Now, what are our next ones? We had this hardness condition that said that the hardness of the final product has to be between a couple of numbers. Okay, so we take that and manipulate it somewhat. So how do we get the hardness? Well, it's you add up it's a weighted average of all of the items in there. Play with it a little bit mathematically, and you're going to get these two constraints. So those two constraints are for your hardness. If you don't see where that formulation came from, stop here and play with the numbers a little bit and see if you can figure out how that came about. And then finally, our final one is saying that the sum of the components minus the amount we get at the end is 0. And this is where I said that, the y isn't really needed here. You could formulate this problem without the y, but we're going to leave it in there for now. You solve it. It's a straightforward linear program at this point. Here is what we get for the solution for January. Solve it again for January, February, and March, and we get that over those 3 months, you can make a profit of $55,870. So that's the easy one. Now what happens if we start to throw the storage in? First thing you're going to notice when you have the storage is that you have to somehow quantify the amount that you don't use 1 month that carries over to the next, which means we can't just use 3 individual problems. We have to look at all 3 months together. So we need variables for the amount that we buy in every month. All of a sudden, we're up to 15 variables for what we buy every month. Missing an I there. So we have the 15 variables that represent the amount of each oil that's purchased every month. But the amount that we purchase every month isn't the amount that's used every month. So we also have to have 15 more variables that represent the amount that's used every month. So now all of a sudden we're up to 30 variables in our equation. And finally, I'm going to put my y back in here. Again, there's a way of formulating this problem without having the y in there, but I'm going to put it in there for now. So the y is the quantity of final product produced in each month. So we are up to 33 variables for this linear program. And now what about the constraints? Well, one of the things to notice first off is that with these variables, the variables were for the amount purchased and the amount used. I'm just going to note here that I can use these variables to figure out the amount that I carry over. So I purchase X11 for oil 1 in the month. How much gets carried over? Well, it's the amount I purchased minus the amount used. What about the carryover from month 2 into month 3? Well, there's my carryover into month 2, from month 2 into month 3. It's what I purchased the first and second month minus what I used the first and second month. Now, why do I say that there's no carryover into month 3? Well, because if you take a look at the structure of the problem, there's no reason to have a carryover. Why would you buy something to carry over when it doesn't produce any profit and you're looking at your profits over the 3 months? Now, this is a bit of a limitation on the problem because in a real business, you wouldn't only look at a couple of months, you would look at a long term. So you would look at carryovers for other months, but this is giving a bit of a handle on what can happen in 3 months if you want to maximize your profits in those 3 months, allowing for carryover. So now what about our objective function? Well, much more complex because we have all of these variables in here. But we can break it down. First of all, we have the amount of revenue. $150 times the number of tons produced every month. So notice there's an inherent assumption here too that the amount produced is going to be sold, that you can sell everything. Okay? So that's an assumption that's underlying all of this. Now, what do we have next? We have the purchase prices. So this next big chunk is what you spend on buying your oils. But we now have a complication in it as well, in that we're allowing storage, but every ton of storage costs $5 per month. So this is the cost of $5 per month minus the number of tons that gets carried from month 1 into month 2, minus $5 times the number of tons that gets carried from month 2 into month 3. So you can think of it, at the end of the month, you get a bill for $5 times the number of tons. So there's our storage cost. So that takes away from our profit. Now we can just rewrite this whole thing, pulling together all of the variables, and we get this thing on the bottom which has all of the variables gathered together. So there's our objective function. Again, dealing with 33 variables. 33 variables, sorry. Now, what about our constraints? Well, a lot of these are very similar. So we had the limitation that the first 2 types of oils, you can only process 200 tons of them a month. But note now that it's not the X's, it's the U's. It's the amount used. Our other 3 oils, you can process 250 tons of them a month. Similar constraints to last time. Again, using the U, not the X. It's not the amount you purchased, it's the amount that you actually use. Our hardness constraints, again, using U's and not X's, because it's the U's that go into creating the final product. So it's the same hardware constraints, but for every month. What are these now? This is saying that the amount used minus the amount produced has to be greater than or equal to 0. You can actually say that these are equal to 0 as well. You're going to actually come out with the same thing in the end. What about these next ones? What does this represent? This says that the amount that you buy in the first month has to be more than the amount that you use. This one is for the second month, and this one is for the third month. So it's basically saying that you aren't trying to use more than you've purchased. So those are new constraints. Now, what about this one? This is for our storage. Our storage says that every month we only have 100 tons of storage. So how much storage do we have after the first month? This is the amount we purchase. This is the total amount we've used, and it says that can be no more than 1,000 tons. So the amount we carry from month 1 into month 2 has to be less than or equal to 1,000. What about carrying from month 2 into month 3? This is the amount of oil 1 of a given oil in a month. Add over all the oils. Again, no more than 1,000 tons carried from month 2 into month 3. This makes a big linear program, but it's actually not that bad for solving. You can take it and solve it in Excel. In fact, I solved it in Excel with the Excel solver to get a solution. Note the benefit you get. As soon as you can buy the storage, as soon as you can store things, you've gone from a profit in those 3 months of 55,000 to a profit of 71,000. So you can now answer questions about, well, if it's going to cost me $100,000 to build this storage unit, how long is it going to take me to get my money back? And you can look at the profits that you make every month and compare that to the cost. And suddenly you have a way of of figuring out whether or not it's worth investing in a storage unit. So that's a very important question for a business, potentially. Also, take a look at the results that we have here. Okay, you see some fluctuation from month to month. Note that there is an inherent assumption in here that you're going to be consistent through the month, that you aren't going to make different mixtures during the month. But note that oil 1 is always 0. You start to see things like this, and if you're the business person, you're going to start to wonder, well, do I ever want to buy oil 1? Under what conditions will that come into my formulation? So looking at the answer, you can start to answer questions that are important to the business. Okay, now we've thrown on a new policy that says we have an initial supply that we're going to have in here. So we're coming into this with 500 tons. So essentially we get some free product right at the start, but we have to save that much for later on. But what's this going to do? This is going to give us some flexibility. So now we may not have to buy more expensive stuff at the start, but we can use what's in reserve as we come into January. So it's adding more flexibility into our problem. So again, what are our variables? Same variables for what we purchase and the same variables for what we use. The variables are going to be the same. What's going to be different is there's going to be a little bit of difference in the constraints. Again, we can use those constraints to figure out how much is getting carried over. And notice that in this one, we have to start to look at how much is not used by the end of month 3. Because our problem now says we have to save 100 tons of each type at the end of month 3. So we have to have an equation here for what's at the end of month 3. So now what about our supplies? Well, our constraint or our objective function is very similar with one difference. We're now storing things from month 3 to the next month. So we have to add on a storage cost. So there's the storage cost of things that are there at the end of month 3. That's the only difference in the objective function. So there's an extra little component in there. And again, simplify it out, gather up all the similar terms, and we have this for our objective function. What about our constraints? Same exact constraints as last time for this. That's the amount we can process every month. Our hardness, same exact constraints, 1 per month for the maximum and minimum. Our supply, well, again, it says that the amount that we use can be no more than what we produce. Now, here's where we get a little bit of a difference. Every type of oil that we have, we start with 100 tons. So instead of saying that the amount that we use has to be no more than the amount we buy, in that first month, the amount we use can be no more than 100 tons more than the amount we buy. Similarly, the second month, a similar type of thing, and the third month, a similar type of thing. So we have that extra 100 tons of flexibility for every one of the oils. Subject 2. Well, here is something that says that the total amount that we have in the first month has to be no more than 500. The amount purchased minus the amount bought, or minus the amount used, is no more than 500. Because we have 1,000 tons of storage, but we started with 500 tons of it already being used. So we only can add another 500 to it. Similarly for the second month and the third month. When you go back to the equations for the storage that you use each month, you'll see that these are the equations that you get. What else do we have here? This is, if you look at oil 1, the total amount purchased over the 3 months minus the total amount used has to be greater than or equal to 0. Now, where's this constraint come from? It says that we start with 100 tons and we have to finish with at least 100 tons. So that means that if you look at over the 3-month period, the total amount of oil one bought in those 3 months has to be at least the amount used, because you have to keep that 100 tons in reserve at the end of March. So this is a new constraint dealing with our storage. And now we can solve this again. It's quite similar to the previous one, but having that extra amount gives us some extra flexibility. In fact, it gives us an extra $10,000 and gives us this first solution. It's very similar, but because we essentially have this free product at the start, we can make we can optimize our purchasing a little bit better. You can buy things when it's a little bit cheaper. Now, if I'm looking at this, one thing that I would note in here is that in the month of February, we have that it buys a very small amount of vegetable oil 1. If I were taking this problem any farther, I would go back and see maybe this is a rounding error, because sometimes if you get some small numbers in there, it's calculation errors, rounding errors that you get when you do a computer solution sometimes. So this may not actually be exactly perfect answer. There may be some rounding errors in here. I would investigate that a little bit more, but this tells you what that extra flexibility is worth to you. All right, that was stepping through a sample problem. In the next lecture, we're going to take another problem that's a little bit messier, that requires some assumptions. We're going to talk about using assumptions and formulating a problem where maybe the information you have isn't quite so clear-cut and dry.